Welcome to the next session of design and analysis of algorithm. So today we will discuss a new concept called NP completeness. So let's understand the motivation behind it. So we have seen up till now lots of algorithms, lots of computational problems, and we have seen different kinds of algorithms to solve them. Okay, but there are certain problems which are extremely hard, and we have failed to find any efficient algorithm for such problems. So it would be nice if we can prove somehow that finding an efficient algorithm is impossible, because then we can stop spending time to solve it, right? Uh, Here the word efficient essentially means that you are looking for an algorithm which works in polynomial time. Okay, so the word efficiency here means that your algorithm has to be a polynomial algorithm. Okay, so it should be bounded above by some polynomial. Now if I know, for given a problem, if I know that okay, I can't find an algorithm to solve it in polynomial time, and I can prove that there doesn't exist one such algorithm, then I don't want to spend time finding an algorithm to solve that problem. So that's why it's very important to understand that whether your problem is very hard or not. Okay, so it's really difficult to prove the fact that your problem is very hard. That means there doesn't exist an algorithm to find there doesn't exist an efficient algorithm, okay, for it. So at least what we can show that our concerned problem is at least as hard as another known problem. Okay, so if I can show that okay, I got a problem, and if I can show that this problem is as hard as a well-known hard problem for which there is no efficient known solution yet. Okay, yet means nobody has found it, but nobody has proven it, there doesn't exist one. Only it is saying that nobody has found an efficient algorithm yet. Then we can start looking for a relatively easier approximation algorithm. Okay, so you say that okay, it's a very difficult problem to solve, maybe I will try to find an approximation to my original problem. I might not get the right result, but maybe a good approximation. Okay, so that's the motivation. Okay, and this entire notion that problem is at least as hard as another known hard problem is captured in NP completeness. Okay, so we need to understand bunch of terms in order to understand how do you prove a problem is NP complete. So first we will start with the basics. So in general, we describe the complexity of the algorithm in terms of the number of items in the input. So up till now, we have described the complexity of an algorithm always in terms of the number of inputs, right? Okay. So here, first what we will do is we will define the input size in terms of the number of bits required to encode it. Okay. So if I have an input, let's say I got a sorting problem, so input is bunch of numbers. So what we are counting is, typically what we count is the number of numbers I am having, okay, a number of integers I am going to sort. But let's say we want what is the number of bits required to encode these numbers. If we want to represent our complexity in terms of that, okay, your input size is defined in terms of number of bits required to represent or encode the input. Okay, so typically what we use is a binary coding scheme, so that each character or integer uses a constant number of bits, and each integer m which is greater than 0 is represented by at most c times log m bits, okay, for some constant c greater than 0. Okay, so what we assume here is that we use a binary coding scheme in order to define the input size. What we do not use is a unary encoding scheme. Okay, so we will not use an unary encoding scheme. So a unary encoding scheme is like you represent 1 as simple 1, 2 as 2 ones, 3 as 3 ones, and so on. Okay, so you don't want to use such an encoding scheme, because in that what happens is number of bits you will use to represent your input becomes too huge. Okay, so your input size is really big. So what we do is we use the binary coding scheme. Okay, so what if you use a binary coding scheme, what we have most of the algorithms we have seen, generally they are polynomial in worst case complexity, right? So in terms of the number of items in the input, typically you can say that the complexity of your algorithm is n to the power k, capital N to the power k, where capital N is the number of elements in your input, okay, and k is some constant. So what we can show is that if you look into any reasonable algorithm that runs in polynomial time, in terms of the number of input items, will also run in polynomial time in terms of the number of input bits. Okay, so if you look into, up till now what you have done is you have analyzed your algorithm in terms of number of inputs. Now in this NP completeness study, what we use is essentially the number of bits required to encode the input, okay, and state the complexity in terms of number of bits. So what it is saying is that all those algorithms which you know are polynomial in terms of number of items in your input, they are also polynomial in time in terms of number of input bits. Okay, that's what this statement is saying. So the complexity of algorithm as a whole remains a polynomial only. So it is n to the power k, where k is some constant. Okay, as long as k could be 5, k could be 2, k could be 500, but still it's a polynomial. So n to the power 500 is a polynomial. Okay, so what we will look into is that this theory of incompleteness is based on something called decision problems. So what are decision problems? They are computational problems for which the intended output is either yes or no. So always there are two answers to your problem, either yes or no. For example, given a string t and a string p, does p appears as a substring in t? There is two answers. There are two answers only, either yes or no, right? Similarly, if you ask, given two sets S and T, do they contain same set of elements? So answer is either yes or no. Fine. Such problems are called decision problems. Apart from decision problems, what we encounter often is optimization problem. So for example, let's say we have the following optimization problem. Given an undirected graph G and vertices u and v, and we wish to find the shortest path from u to v. So you are given a graph which is an undirected graph G, and you are given two vertices u and v, and you want to figure out what is the shortest path from u to v. So you have to minimize the length of the path. So it's an optimization problem. Okay. So given an optimization problem, you can convert it into a decision problem in the following sense. You can state your optimization problem as a decision problem. For example, in this case, you can say, given an undirected graph G and vertices u and v and an integer k. So you take an integer k and you ask the question, does there exist a path from u to v consisting of at the most k edges? So it's not asking the question which one is the shortest path or how many edges are there in the shortest path. Rather, it is saying that, okay, I give you a number k. Does there exist a path whose length is shorter than k? Okay. So that's what is the corresponding decision problem, because the answer to this question is either yes or no. Whereas in the previous case, when it was an optimization problem, you have to find the shortest path and give a number, right? That okay, the shortest path has so and so many edges. Okay. So since NP completeness deals with decision problems, often it becomes a necessity to pose an optimization problem as a decision problem in the following way. Okay. Okay. So now we will discuss a particular notion of problems and languages, which is very important to understand. So an algorithm A is said to accept a string X if A outputs yes on input X. So you give this string X to this algorithm A, okay, so that it takes this input, a string, okay, and it will say that okay, yes, it accepts the string X, okay. So given a decision problem, all of its input instances can be encoded as a string, right? You are given a decision problem, you choose any decision problem. Any of its input instance can be encoded as a string. Remember, an input is nothing but bunch of bits, okay, in a particular encoding. So as we said that we are going to use binary encoding scheme, okay. So given a decision problem, all its inputs can be encoded as a string. And you take all those strings and you call them that it's a language which is collection of a string, okay, L. So we'll say an algorithm A will accept a string means it correctly solves the problem. So every problem is encoded as a string, okay, and what happens is it can solve the problem and give the decision to the problem as yes, okay. So and the answer to the decision problem is yes, okay. So with this notion, so for a particular string, an algorithm will accept a string. So an algorithm is think of it as a box, okay. It will accept a string, which means what it will do, given a particular string X, it correctly solves the problem and answers the decision problem as yes, that yes, this problem is coming under the yes instance. That means for every decision problem, remember there is a yes answer or no answer, okay. For example, we said that yes, P is a substring of T, okay. So given an encoding of your problem, that is given an encoding of P and T, your algorithm will say that okay, given some P and some T, okay, that is a string. If P is a subset of T, then it will say yes, okay. So that's the string we are talking of. Then those set of collection of strings will make a language, okay. So an algorithm A is said to accept a language L if A output yes for each of the strings in this language L. So for each X belonging to L, it will output yes and it will output no otherwise, okay. So we say that this algorithm accepts a language L if A outputs yes for every string in this language L, okay. What is a language? Language is nothing but a collection of strings, okay, fine. And we have already seen what does it means to be accepting a string, okay. When do we say that an algorithm accepts a string? It takes an input, which is the string, and this input, for this input the decision taken is yes, okay. That's what we are saying is such set of strings together make a language, and the algorithm which accepts this entire language is the one which accepts every string of that language, okay. So now we will define the complexity class called P. So it is nothing but the set of all decision problems or languages. Now you can see that corresponding to decision problem there is a language L, okay. So the set of all decision problems, all languages L, that can be accepted in worst case polynomial time is called the complexity class P. So here is an algorithm A which can solve your problem, okay, decision problem in polynomial time. That means it will say yes in polynomial time given a string which belongs to L. Such class of problems is called P. Okay. So note that the definition of P doesn't say anything about the running time when an input has to be rejected. Okay. So it's not in the definition itself, it is not stating anything how much time it takes to reject it. To accept it, it says that it will take polynomial time. So the claim is that let's say L be a language in P. That means it's the decision problem for which there is an algorithm which works in polynomial time. So the language corresponding to that decision problem is L. So let L be a language in P, then you can show that its complement language L prime or L bar is also in P. Okay, so you can show that its complement language is also in P. How? So let's look at the sketch of this proof. Let's say A be the algorithm for the language L. So remember, L is what? L is in P. You know that. You want to prove that L complement is also in P. So L is in P means there is some algorithm A which takes Pn amount of steps, maximum Pn amount of steps. Okay. So that's the worst case number of steps it requires for any input of size n. So now given that, we will design a new algorithm for A prime which can tell, okay, which can tell that whether a particular string belongs to L prime or not in polynomial time. How? So here is the new algorithm A shown as a box. What it does, it takes an input x, okay, and then it gives this input to the algorithm A. So within algorithm A prime, you run A. And what you do, you run A for Pn steps on x. That means you know that if Pn is the number of steps required for the algorithm to run at the maximum for any input of size n. So what you do, you take A and run it on x, where n is the size of x. Okay. So if x belongs to L, so if x belongs to L, then this algorithm A will accept x, right? Which means that if x belongs to L, then you know that x does not belongs to L prime, right? So you can answer this question whether x belongs to L prime saying that no, x does not belongs to L prime, right? Okay, because x is in L. Okay, so x is not in L prime. Other way around, I take x, okay, and let's say x is not in L. Then what happens? I will run A on x for Pn steps. That's the maximum number of steps required to run on any input of size n. And if by Pn steps I have not reached to a conclusion, then I say that okay, that's the maximum number of steps I require to get a yes answer. That means that x does not belongs to L. That means I will say that yes. So my algorithm A prime will say yes, x does not belongs to L, which means x belongs to L prime, right? Okay, so you get the yes instance of x belonging to L prime. So that means what we are saying here is that if I take x belonging to L, then I will run P this algorithm A on X. It will say yes. If it is yes, then I will say no. A prime will say no. That means X does not belongs to L prime. Right? Okay. If X belongs to L, A prime is doing what? It is running A on X for Pn steps. It is not done by running Pn steps, so it will say no, it is not done. And then it will say that okay, yes, then output yes, which means X belongs to L prime or L bar. Okay, fine. So I can now accept if X is not belonging to L, that means X belongs to L bar, then I am going to accept that. Okay, how much time I am spending here? Polynomial time, because A takes polynomial time to run. Okay, so your L prime is also in P. Okay, fine. Now we will, so that's the class called P, polynomial class. Now we will show there is another class called NP. Okay, so now if a language L can be verified by an algorithm A if given any string x belonging to L as input, there is another string y such that A outputs yes on input z is equal to x plus y. So here x plus y, this is essentially a concatenation operation. So what it is saying? I require two things. A language L can be verified by an algorithm L. So if there is a language L which can be verified by an algorithm A, where you need to give an input from the language L, so x belongs to L, and you take help of another string y together, so x plus y is the total input, your algorithm A outputs yes on this input x plus y, okay, which is equal to z. So this string, extra string y, which we added, is what is called a certificate for the membership in L. Okay. So the set NP is nothing but the set of all those languages L defining decision problems. So we are talking of only decision problems here. So NP is the set of all languages L such that L can be verified in polynomial time. That means this algorithm A, which takes x and takes help of another input y and decides whether whether the problem is an yes instance or not, okay, in polynomial time, that kind of problems we are talking of, that set of problems is what we called as NP. So NP is the set of all languages L defining decision problems such that L can be verified in polynomial time. And note that there is a deterministic algorithm A. So we are talking of a deterministic algorithm A that for any x belonging to L verifies in polynomial time using some certificate y that x is indeed in L. So what is it this algorithm A is doing? Given x belonging to L and a certificate, it can verify in polynomial time using the certificate y that x is indeed in L. Okay, so x is definitely belonging to L. Looking at that y, it can say. Okay, so that's the complexity class NP. Now notice that this is called NP because it turns out to be, the full form of it is non-deterministic polynomial. Okay. Now where is this non-determinism is coming from? there is an alternate definition to NP, this complexity class NP. But I'm not going to discuss it in this class because you require some understanding of theory of computation in order to understand that definition. Okay, so I'm not going into that definition, rather using an actual definition which is based on non-deterministic polynomial, what we call as a non-deterministic polynomial Turing machine. Rather than doing that, what we are doing is we are using a verifier in order to define this complexity class called NP. Okay, so notice that first of all, P is a part of NP. Okay, so for a particular problem P, which can be solved in polynomial time, definitely it can be verified also in polynomial time. Okay, so definitely P is a subset of NP. Okay, so next class we will see that how can we show certain problems as in class NP. Okay, we'll stop at that. Thank you.